So I'm glad to present Arthur Bartels. So Arthur got his doctoral degree in 1999 from the University of California at San Diego. Now he held positions at the University of Münster in Germany, at the Imperial College in London, no? And then since 2008, he's professor at the University of Münster in Germany. Today, he will talk about K-theory and actions on Euclidean retracts.
Okay, thank you for coming. It's a great honor to give this talk. I'll be talking about K-theory of group rings, and to motivate you, I want to start with a very classical theorem of Wall that tells you, if you want to know about some space, that it's homotopical to a finite CW complex, that this can be detected by K-theory. So there's an invariant tau x in K-theory that's zero if and only if our space is a finite CW complex. Well, some more explanation. Being a finite CW complex means we can build our space just using finitely many cells. To get the theorem going, we already need some finiteness assumptions, namely the space should be finitely dominated, so it embeds as a homotopy retract into some finite CW complex. And the K-theory group we're interested in is the Grothendieck group of finitely generated projective modules. More precisely, we have to divide out the free modules. So this group kind of knows about all the projective modules modulo free modules. So it knows whether there are projective modules that are not stably free. You could complain that I didn't tell you what tau of x was, what this invariant is, and this might be difficult to compute, but even if I don't tell you, you get a corollary, namely, suppose this K-theory group vanishes, then the invariant has to be zero, and we get the conclusion that x needs to be a finite CW complex. Okay? So then, of course, the question now becomes, instead of computing tau, we still need to compute this K-theory group. And there's many similar examples where algebraic K-theory tells you something about topology and manifolds. For example, the S-cobordism theorem expresses the triviality of H-cobordisms in terms of an invariant in the Whitehead group that in turn is derived from K1 of group rings. And more fine structure of manifolds, if you want to use the machine of surgery theory, that kind of translates questions like are two given manifolds homotopical into questions about L theory. So now you have to understand L theory groups of group rings. Okay, and a good place to start with results about such calculations is the following beautiful theorem of Farrell-Jones. So if G is a closed manifold of strictly negative sectional curvature, then they prove that the two groups we've seen are in fact trivial, so we get these geometric conclusions that I alluded to. So this theorem starts out with a geometric assumption on the group, or on the manifold to start with, and then uses the geodesic flow to get a conclusion about the algebraic K-theory of the group ring. This sort of result was conjectured for Schrank for all fundamental groups of spherical manifolds, but even stronger, it's possible that it's true for all torsion-free groups. I mean, no torsion-free group is known where any of these two groups are non-zero. And to connect it to what is going to come in the remainder of the talk, I want to point out that in the situations we have an interesting action of G on an ER, namely the ideal compactification of the universal cover of M. Right? The universal cover will be an Rn. If we compactify it, we get a disk, so we get an interesting action of our group on this disk. So I just started out with this theorem, but they proved many more theorems, and also in the context of L theory. So there are results for non-positive curved manifolds for groups with torsion. And moreover, sort of their idea also led to a conjectural picture of what K-theory should be, K-theory of group rings, and that's the Farrell-Jones conjecture. And to explain what the conjecture means, what the conjecture says, I want to talk a little bit about assembly maps. Oops, this is... Okay, so imagine you try to understand the K-theory of this group ring Rg, and one way you could try to understand it is you pick some subgroup F that maybe is easier to understand, and you map it into and see what you get, right? So one way to understand the right-hand side is by probing it with subgroups. Or you could have, you could have a whole family of subgroups. And then test all of these, and then on the left-hand side, you should take the co-limit over all these subgroups. But in general, it's not quite correct to just look at K0 on its own. You should look at all of K-theory at the same time, and the way to do this is to use the K-theory spectrum. So, I'll keep on further. So now, instead of having this algebraic group K0, we have the K-series spectrum of R, and then we can do the same thing now with a spectrum instead of these groups. And then the co-limit on the left-hand side becomes a homotopy co-limit. Right? And the game is you try to understand that the right-hand side in terms of subgroups, and the family of subgroups you want to consider should be as small as possible. And often it's beneficial if you make inductive arguments so maybe you can get down to some family Fn, but then you try to make the family smaller to make the left-hand side more computable, more understandable, and to know in the end more about the K-theory of the group ring. Okay, and Farrell-Jones, their conjecture tells us exactly how far we're supposed to go. We're supposed to be able to reduce this down to the family of virtually cyclic subgroups. So the conjecture says, understanding K-theory of group rings, there's a way to get at it just looking at the virtually cyclic subgroups of the group and then putting all this information in an appropriate way together. And the virtually cyclic subgroups already showed up in the first result. I've shown you about the vanishing of the Whitehead group and the K tilde for fundamental groups of negatively curved manifolds. This argument also proceeds by first reducing the question to cyclic subgroups and then applying an algebraic argument. Okay, and in particular, so this conjecture general is what they have done before. For a torsion-free group, there aren't all that many virtual cyclic subgroups, so all you have to consider is infinite cyclic subgroups, and then there is an algebraic argument what tells you what the K-theory is, and you get this conclusion that you have these vanishing results that then give you geometric applications. As I mentioned before, we're also interested in L-theory, but this works formally really very similar, and moreover, the results are also now all the same. So for the L-theory version and the K-theory version of the Farrell-Jones conjecture, there's not a real difference anymore. On the other hand, the Farrell-Jones conjecture has a famous relative, the Baum-Kohn conjecture for you reduce C-star algebras that is formally looks very similar. You look at a different family of subgroups. You're supposed to sort of reduce even to finite subgroups. But as far as positive results are concerned, this is rather different. So the methods between the two conjectures don't transport very nicely. Okay. The next thing I want to do, I want to explain a criterion that implies the Farrell-Jones conjecture. And you can think of this as sort of an axiomatization of half of the proof of the first result of Farrell-Jones. Okay, so I'll start by reminding you about the notion of amenability for an action. So an action on a space, you should think a compact space, is said to be amenable if it compares nicely to a space that's easier to understand, namely the space of probability measures on G. Right? Ideally, we would like to map our space, we would find an equivariant map to our space of probability measures, but that's too much to ask for. So instead, we're asking for a sequence of maps that aren't quite equivariant, but the mistake we're making gets smaller, right? If we first apply F and then G, or if we apply first G and then F, the difference is supposed to go to 0 as we change this map Fn. Okay. And this characterizes an important class of groups, namely the class of exact groups. The group is one characterization of what it means for a group to be exact is that the Stone-Čech compactification of this group is amenable, satisfies this condition. And this comes up in connection with the sort of conjectures I'm talking about, not quite with the Farrell-Jones conjecture, but exact groups are known to satisfy the Novikov conjecture. But this is sort of an infinite dimension result because it goes through the machinery of C-star algebras and the Baum-Kohn conjecture. There's no sort of direct algebraic way to get this result. Okay, and the class of exact groups is really a large class of groups. So here are some examples, and because they come up again later, let me point out that mapping class groups are known to be exact. And very recently, Bistvina, Gaudiel, and Horbes proved that the auto-automorphism groups of free groups are also exact. In particular, the Novikov conjecture holds for these groups. So now, as I said, so in this case, we sort of need infinite dimension machinery, and it's not amenable to algebraic K-theory directly. In this case, we need to go to a finite dimension setting. So I'm going to change the definition to get some finite dimensionality. So I'm replacing the space of probability measures with just a subspace of those probability measures that are supported on at most d plus 1 points. Right now, we really just have a simplicial complex that we want to map to, this space delta d of g. And then we say an action is d amenable if we have the same thing as before. We find a sequence of maps to this nice organized space that isn't, I mean, every single map isn't quite equivariant, but in the limit, this looks like equivariant maps, right? That the mistake we make gets smaller and smaller. Okay, and this also characterizes a well-known class of groups, namely those groups with finite asymptotic dimension. A group has finite asymptotic dimension if and only if the action of the group on its Stone-Čech compactification has this property, is what I call D amenable. And again, this is a still large class of groups, and I've shown you a list here. But note, the group of automorphisms of the free group is no longer on the list. And I also want to point out what's maybe not quite obvious, but not difficult to show, that if we have this property, if an action is D amenable, then also all isotropy groups for the actions need to be finite. For amenable actions, it would just force the isotropy groups to be amenable. But now with this finite dimensionality, the isotropy groups have to be finite. Okay. And the sort of space we're going to need in connection with the Farrell-Jones conjecture will be much nicer than the Stone-Čech compactification of a group, and this will force some isotropy groups onto us. So we'll need a version of the definition that allows for some isotropy. And here it is. So now we start with a family of subgroups, which we think of the isotropy that we want to allow. Sorry. This is not going well. Okay. As we have a family of subgroups, and think of this as the isotropy that we want to allow, and we just take a set that has isotropy in this family, right? We just take the disjoint union of all the orbits, and then now we take probability measures on this set instead of the group, right? The group, we took the group, we had a free space, and now we have some isotropy, and then we do the same thing as before. We ask for a map to the space of probability measures with the most d plus 1 points. Ideally, we would like this map to be equivariant, but instead we're going to allow some mistakes, but they should go to 0 as n tends to infinity. And I want to point out that similar notions have appeared in different contexts, in particular in connection with the classification of nuclear C-star algebras in the work of Winter. And there are further variants of these notions. Okay, and just to have an easy way to say things, I'm not really interested in the exact value of the correct D. It's just important that there's some finite D. So for this reason, I'm going to say an action is finitely amenable if we find some D such that it's D amenable for DF amenable for this D. Okay, and to I want to at least explain a little bit the connection to negative curvature of these notions. And for those who haven't seen it, I want to explain to you that the action of the free group on its boundary is amenable. Okay, so how do we understand a point on the boundary of the free group? Well, we pick a ray towards this point starting at 1, and then we can cook up a probability measure by just taking an initial part of this ray and taking the Dirac measures for the first, say, n+1 points along this ray, normalize accordingly, and we get a probability measure on G. Okay, and now we understand how this relates to the group action, how large the mistake is if we apply a group element. So if I apply a group element G, you know, my array is now going to end up in G times the point we started with, and it's going to start at G. And we need to compare it to what happens if we pick the ray starting at the identity. And of course, we get this picture, and the two rays are going to overlap for most of the time, and the mistake is just a very small mistake, right? And in this picture, those 4 red dots. And as n increases, the mistake goes to 0 since we're dividing by n. Okay, so here's now the criterion. It's formulated in terms of action on Euclidean retracts. Euclidean retract is a compact space that embeds as an honest retract into some Rn. So in the easiest case, this could be a disk. Okay, and a theorem I proved a while back with Wolfgang Glück and Holger Reich is the following. If we have some action on a Euclidean retract that has this property that's finitely F amenable, then this group satisfies the Farrell-Jones conjecture relative to this family that we studied, meaning that this assembly map that uses all the subgroups from the family to the group is an isomorphism, or if we talk about spectra, an equivalence. And when we did this, this was to prove the case of hyperbolic groups. Right, because in this case, this criterion is satisfied for the action on the compactification of the Rips complex. And more recently, I generalized this to relative hyperbolic groups. In this case, you cannot expect the Farrell-Jones conjecture to hold directly, but you expect to reduce it to the parabolic subgroups of the relative hyperbolic groups. And as Dennis Olsen pointed out in his talk, there's an alternative proof via Dehn fillings due to Antolin, Collin, and Gandini, at least if you assume that the parabolic subgroups are all residually finite, as were all groups in the previous talk. Okay. And what I want to talk in some detail about is another application of this theorem to mapping class groups. So the mapping class group acts on Teichmüller space, and Thurston compactified Teichmüller space to a disk, and together with Mladen-Bistvina, I proved that this action again has this property, it's finitely F amenable, where now F is the family of isotropy groups for the action, actually the family of virtually isotropy groups for this action. Really, one cannot hope for more, because as I said, the isotropy groups for the action will have to show up on the right-hand side. But the isotropy groups for this action are well understood. These are almost mapping class groups of surfaces of lower complexity, so you can get inductive argument going and get the Farrell-Jones conjecture for the mapping class groups. As I said, I want to explain this in some detail, but before, let me answer the obvious question by saying that I don't know. Namely, what about the group of outer automorphisms, those free groups? There is also an action on Euclidean retracts. So one might hope that the theorem can be applied, but we don't know that this action is finitely F amenable for some interesting family F that would enable us to prove something about the K-theory of the group. Okay, so I want to talk a little bit about how the proof goes for the mapping class group, but instead of discussing directly the mapping class group, I'll just talk about a toy example, namely the action of SL2Z on the boundary of hyperbolic 2 space. And I'm only going to talk about the action on the boundary because this is usually where the interesting where the problems lie. Once we've proven that the action on the boundary has this property, it's not difficult to extend it to the action on the compactification of in this case, hyperbolic space. Okay, and the additional difficulty this has over, for example, the free group or hyperbolic groups is that in this case, the natural action for SL2Z on hyperbolic 2 space is not co-compact. And the natural way to deal with this failure of co-compactness is you could look at horoballs in H2, and then the complement of those will be co-compact, and you kind of know that the problems have to come from these horoballs. We're going to do something slightly different. We're going to look at the action of SL2Z on the ferry graph, which I've embedded here into H2. The picture only shows part of the ferry graph. You would have to keep drawing to get the whole ferry graph. Okay? But the vertices of this graph correspond exactly to the horoball. So it's kind of a combinatorial picture for the structure for the possible structure of horoballs. Okay, so the additional information you can extract from this picture is now, again, we have a point on the boundary that I labeled Xi1 here. And then instead of going directly to this point via a geodesic in H2, we travel along the ferry graph. And then at each vertex that we meet along the way, we can pick out a number that asks how many triangles did we skip over, right? In this case, we skipped over 1, 2, 3, 4 triangles before we kept going. Okay? And one says that the angle of this red curve at this vertex is 4. Okay? And I mean, angle is maybe a slightly misleading word. It's not a number between 0 and 2 pi. It can be infinite. And it kind of measures how long a geodesic from x0 to Xi1 would spend in the horoball corresponding to V1. Okay. So large angles means we're going through a horoball for a long period of time. Okay, and here's another example of where there are different angles, just to illustrate, right? So for the blue curve, for the blue path, the first angle here is 1, and the next one is 2, and then I didn't calculate anymore. Okay. And the key properties that one gets from these angles is first, they again detect whether or not we're in the co-compact part of the space. Right? If a geodesic from x0 to Xi1 does not stay in a co-compact part of H2, this means we'll have to penetrate horoballs further and further, or in this translation it means angles have to become larger and larger. That's one property. And the other is that these angles kind of behave well with respect to the group action. I mean, if I act, then of course the angles don't change. But here in our picture, we kind of fixed the base point x0, right? So if I fix x0 and then I act on the vertex and on Xi, the angles change, but they only change in a controlled amount. So this gives us kind of a very combinatorial and rigid picture for how points on the boundary interact with the horoballs. Okay, and then the argument roughly goes as follows. I mean, we want to define our map on the boundary of hyperbolic space, and we're going to divide it into 2 parts and use different techniques on these 2 parts. I mean, first we look at sort of the co-compact part. So assume we have a point on the boundary such that if you travel to it, all angles are small. The collection of all those points behaves still as in the co-compact situation, so you can use arguments that I didn't really tell you about, but that there is a packing argument that can be used in this situation. Okay. But then not all angles are small, so you have the rest where the angles are large, and in this case, you can kind of pick out the first angle. I mean, you have to pick some scale, theta here, and then you can pick out the first angle, the first vertex where the corresponding angle is very large. Okay? And this singles out the vertex for you, and then the action of SL to Z on the set of vertices has just virtually cyclic isotropy. So this is a set we can use in our target. Right? We can identify this with orbits from the quotients G by V, with V virtually cyclic. Okay, so that's all I wanted to say. It doesn't quite work. I mean, you cannot quite use these maps because the notion of first is kind of a dodgy notion. I mean, if you just change a little bit, then somebody that was where the angle was almost bigger than theta, but not quite, could after changing it become bigger than theta, and it changes which one is the first vertex. But there are tricks using this rigid situation to actually then produce a map that has these properties, that is almost equivariant. Okay. And for the translation to the mapping class group, I just want to give you this table. So we replace SL to Z by the mapping class group. We replace hyperbolic 2 space by Teichmüller space. The boundary of hyperbolic 2 space becomes the boundary of Teichmüller space, also known as the space of projective measured foliations on the surface in question. And the union is then the Thurston compactification. So one needs to study the action on PMF. And in this situation, one has sort of analogs for the Ferry graph and for the angles we discussed. The Ferry graph, instead of the Ferry graph, we used the curve complex consisting of the curve complex introduced by Maser-Minsky, consisting of curves in the surface, and then there is an edge between two curves if you can realize the two curves disjointly in the surface. And an important theorem of Maser-Minsky states that this complex is hyperbolic. But it's not quite enough just to look at the curve complex for the surface we're looking at. You also have to look at all curve complexes for subsurfaces of your given surface, sigma. And then there are projection maps that produce from points in Teichmüller space or on the boundary points in these curve complexes, and you can measure distances in these curve complexes, and those are the projection distances of Maser-Minsky, and have been used, for example, for the QI rigidity of mapping class groups. Okay, in our situation, nevertheless the action on these curve complexes is still too complicated to apply this argument that we had for the Ferry graph before. But there is a further construction, namely the projection complex from Bestvina, Bromberg, and Fujiwara, that kind of organizes all these subsurfaces in a nice way, very similar to what happens in the Ferry graph. And in particular, then for the action on the projection complex, one has again the two key properties that the Ferry graph had, and this can then be used to run a similar argument for the mapping class group. Okay, that's what I wanted to say about the proof for the mapping class group. But I don't want to leave you with the impression that the theorem about finitely F amenable actions on Euclidean retract is sort of the last word on the Farrell-Jones conjecture, because they're very easy groups where it seems that this property is not satisfied. Namely, abelian groups are already a problem. So if you take Z2 acting on R2, then you compactify R2 naturally to another disk. But now the action on the boundary is trivial, meaning the stabilizers are the whole group, and then we have no chance of testing that this action is finitely virtually cyclically amenable, right? I mean, we cannot. I mean, there's no way to get down using this this question. But in this case, so there is an perturbation one can do. So instead of compactifying R2, one looks at large balls in this picture, and then looks what the action does. Of course, I mean, it does not act on these balls because points are taken out by the action, but we can just radially project back to the ball and get still kind of an induced map phi of g on the ball, that if a point by g is not translated outside the ball, then we use what g does, and if it is moved outside of our ball, then we project him back. Oh, right. I wanted to point out that sort of, I mean, before the problem was every point is fixed, every point is on the boundary is fixed by the whole group, right? But if you look at this picture here, if you look at this picture here, now, I mean, the boundary is now just this finite circle, and almost no point is fixed by this action. It's just one point remains fixed, this one. I mean, we move him up, we project him back down. He's fixed. Every other point moves along the boundary. So the situation has improved, and in fact, this turns out to be useful for the Farrell-Jones conjecture. Of course, the disadvantage is that, right, if we first apply phi g and then phi h, we no longer get necessarily what phi h g would do, so we don't have an action of our space, so we have a homotopy action. Okay, a homotopy action consists of the following. We have for every group element maps, and then we don't ask for these maps to play exactly right with the group action, but we ask for this to happen up to a homotopy. So we specify a homotopy between these two ways of associating a map to G and H. And moreover, the action should be homotopy coherent, which means that there are lots of further homotopies that sort of, right? I mean, if you have these homotopies from G and H, if you have now 3 group elements, there's a natural thing you might ask your 4 homotopies, is it then? The 4 homotopies to satisfy, they're not going to be satisfied, but they're going to be corrected by further homotopies, and this keeps going, and so on. Okay, and then we can also try to ask for the same thing as before in this almost equivalent maps. You can also ask for this with respect to a homotopy action, namely. All right, we still, I mean, now it's better to also allow for the action to vary. For example, in our previous example, we picked a radius for the size of this ball, and in the end we want to let this radius go to infinity. Okay, and then this gives us not just one homotopy action, but a whole sequence of homotopy actions. Okay. Okay, and this is what we ask for. Well, we have a sequence of homotopy actions, and now we ask for maps for, I mean, the sequence of actions is going to be on a sequence of spaces. We're going to ask for a sequence of maps to the space we had before with the correct isotropy, and the first equation is the same equation, the first requirement is the requirement we had before. The maps should play well with the group action. If I first apply what I can do with G on X and then Fn, I should get something close to what I get by first applying Fn and then G. Okay, and then the same thing needs to hold for the homotopy. So in particular, if I apply the homotopy between G and H, and then move to this target space delta D, then I should be close to what I would have gotten if I mapped with G of H. Okay, and this leads to a more flexible condition that still implies the Farrell-Jones conjecture. There was some preliminary version of this theorem that I proved with Wolfgang Gluck when we attacked ket-zero groups, and Wegener sort of built in the coherence in the theorem and then got the full Farrell-Jones conjecture out of this. And moreover, this is a building block for many further cases of the Farrell-Jones conjecture, and I only prepared the sort of last result of this, namely the following beautiful result of Lück, Kammeyer, and Rüpping. They show that all lattices in Lie groups satisfy the Farrell-Jones conjecture, and it uses as a building block this kind of condition. Okay, and that's all I prepared. Thank you.
So is there any questions or comments?
So I was listening to the last talk, and I'm wondering if you could prove the same thing for the profinite completions of these groups.
Well, the profinite completions are topological groups, right? And then it's not even clear what the statement should be. Like you would have to define algebraic K-theory of group rings over topological groups. It's not quite clear what that's supposed to be. And then moreover, the profinite completion would be a compact group. So in the context of topological groups, you would kind of think that you need to work relative to all, at least work relative to all compact subgroups.
So there's the discrete group, which is profinite, and there's the continuous group, which is profinite. Presumably the K-theory of them is connected, but I was talking about the discrete group.
So you want to leave the profinite completion as you want to view the profinite completion as a discrete group. Yeah, I don't know.
For example, they're torsion-free.
Pardon?
For example, they could be torsion-free groups.
Yeah, I don't know if this passes to profinite completions.
Any other questions? Okay, let's thank the speaker again.